Okay, so without further ado, let us start the talk, the lecture now. This lecture video will actually last for about 1 hour and 18 minutes, more or less. Okay, so I believe all of you have already signed. 1, 2, 3, 4, 1, 2, 3. Yeah, already in. Okay, just give me a second. Yeah. Okay, I'll start the the video now. Uh, this chapter is
This
in
chapter
fact
is
the
in fact the
continuance
continuance
of
of
the
the chapter
chapter
6,
6,
the
the
DC-DC
DC-DC
converter.
converter.
This
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 chapter
chapter
7 is
7 is
called the
called the
switch mode
system
power
power
supply,
supply,
or
or
in short
short
SMPS. Now, the chapter 6 we have actually discussed about the step down and also the step up converter in general. So this one will bring you into another this similar thing. Okay. However, this one can be either using a transformer or without a transformer. If we are using a transformer, meaning that we have the uh, this safety measurement, and also with the transformer, we can actually use it to adjust our this required or the desired output voltage. Yeah. Uh, but in my opinion, with this DC-DC converter, we can actually control it through the duties ratio. So we not necessarily need to have the transformer if safety is not an issue. Yeah. And also in this SMPS chapter, uh, we can actually divide it into two categories: non-isolated and also the isolated uh, version. Uh, in this chapter here, we discuss only the non-isolated. Okay, so normally for a non-isolated switch mode converter, uh, in this case here, we are using only one single switch to accomplish the task. Okay, of course, this one single switch may come together with some other component, like the diode, inductor, and also the capacitor. Okay, the diode normally is one only. However, the inductor and also the capacitor can be either one or two in use. Yeah, right. So we will discuss.
Can you hear my this voice? The voice, the video voice. Can hear it or not? Can Okay, thank you. Then I continue.
Four type of this SMPS here, namely boost, buck boost, and also the choke converters. The buck is actually the step down converter. Boost is actually the step up. Buck boost meaning that this converter allow us to have the output voltage which is either higher or lower than your input. Then the choke converter is actually a more advanced version of the buck boost converter. Yeah. So let us take a look on the buck regulator here. Right. In this circuit here, you can see that how the buck regulator is actually operate. It's actually mainly due to the uh, turn on and turn off of your transistor Q1 here. So when the transistor Q1 is actually turns on by applying a getting pulse here, So the current flow through from the Vs to the inductor to the load in this direction. So in this case, you have the mode 1. So this is the mode 1, okay, when the switch is on, okay. So inductor is actually charging up to the load here, okay. And when the switch is actually turns off, meaning that there will be no current flow from the supply because the Q1 here is actually off. So you have the one in mode 2. The one in mode 2, we have only this part of the circuit here, right? So when the inductor already charging up during the mode 1 when the switch is turned on. So at mode 2 here, the inductor will release the energy to continuously supply the energy to your load here in this direction. Being that your diode DM now is in forward bias, okay? Or in this case, we can simply say it's actually a short circuit, but it should actually provide the direction to your inductor to discharge, which is in this clockwise direction. Okay. Of course, when your this transistor Q1 during a time when it's turned on, your this DM here is actually reverse bias, so it's in fact open circuit. Okay. So if we are taking the consideration of the waveform here, this one is actually due to the voltage across your diode here. So when the transistor is turned on, diode is actually in reverse bias, so you see the voltage appear across the diode. Okay. T2 is when there is no when the diode is in forward bias, so it act like a short circuit or it is in conducting uh, region or forward bias. So there is there will be no voltage measure. Okay. In this case here, during the time at time t equal to 0 for time t1 here, the inductor current is actually charging up. So the IL or the inductor current is rising up. And until this point here, the switch is turned off, so the current is actually fall down. Okay, this negative slope here represent the inductor is releasing its energy to supply to the load. Okay, so this one is actually your input supply current. The input supply current when the time t1 is turned on, they are in series with the inductor current, so that this value should be equal to this value here. However, when the transistor is actually turns off, the input supply is actually separated from the rest of the supply. So during the time t with t2 here, you see that there is no current appear in your this supply current waveform. Yeah. This one is your capacitor current. The capacitor current, now what we are actually studying here is actually all under the steady state condition. The transient response is or transient condition is not taken into the consideration. Yeah, so that we can see that the initial value for the steady state when the capacitor when the switch is actually turns on, your capacitor current is actually is equal to I1 minus IA. I1 here is in fact the minimum value of your inductor current. To be more exact, this one should be equal to IL1, okay, which is true, okay. And when it is in the maximum value, that means that your this I2 is your maximum value of your inductor current, which is equal to IL2, okay, minus I1, because based on the circuit here, we can see that, yeah, the current flow through here, through the inductor here is split into IC and IA here. So based on the KCL here, the IC equal to the IL minus IA. So this is the fluctuation of your this output voltage or your capacitor voltage. Right. So you can see that for this current here, the upper triangle here, which is in positive, that means that the the current or the energy or the power is added into your this capacitor there. Okay, when it is in a negative, it will be actually remove the energy, the charge from the capacitor. That is why so your this capacitor voltage will be fluctuate with this delta ripple here, delta VC here. So your loop current supposedly should be a constant value. Okay. So let us take a look on the equation here. So the inductor voltage EL here is equal to the rate of change of the current multiplied with its inductance, which is equal to L di over dt. This is the general one. So by using the this KVL for time t1, meaning that during mode 1 here, okay, during mode 1 here, you can see that the voltage here, okay, is then equal to the summation of this voltage plus this voltage here. So that is why you have this one. If I bring over the VA from the right hand side to the left hand side, it becomes my negative. So we have this equation in 44. If we arrange it for the T1 here, we have the equation here in 45. Okay. The same thing applied to the mode 2. When the mode 2 is actually on, meaning that your switch is turned off. So you can see that your VA is in fact equal to L delta I over T2. Okay. Why is negative? It is because you can see that this one is the VS equal to this one plus VA. So if I bring my VA from right hand side to the left hand side, it becomes negative. And there is a negative here for your this inductor voltage because it is now the current is actually discharging, and also you can see from the waveform here it's actually in a negative gradient here, so you have a negative there. So arrange it, you have the equation 47 for your T2, right? Now, delta I is in fact the difference between the maximum and minimum value of your inductor current, which means that equal to I2 minus I1. And if we are equating the delta I for the equation 44 and 46 together, we form this equation here. And we substituting that the T1 is equal to Kt and T2 is equal to 1 minus K times T here into the equation, we form this equation, which is our output average voltage, VA, and is equal to KVS, where K is your duty cycle, VS is your supply voltage. Yeah. Assuming that the system is lossless, meaning that the input power is equal to the output power, so we can obtain the input supply current IS equal to KIA, or in equation 49. Now the switching period T, yeah, is equal to T1 plus T2. So if we are substituting T1 and T2 from the previous two equations, we have this one, and we can factorize it to form the equation in 50 here. So if we rearrange it for the delta I, we can then use this either equation 51 or 52 to calculate the delta I. Now 51 is with the VA together, but this VA can be eliminated based on the equation that we obtained in 48, which is VA equal to KVS. So we substitute inside there, we have it in 52, right? Now, also under the KCL here, we know that inductor current IL equal to the capacitor current plus the load current IO. Now, if we assume that the load ripple current is very, very small and can be ignored, meaning that my delta IL is then equal to my delta IC here. So the average, the capacitor current is then equal to IC over 2. The average divided by another 2. So the average is then equal to I delta I over 4. Okay. So this one can be actually reflect from the triangular waveform here. You can see. Yeah. The capacitor voltage VC can be expressed in the integration of your capacitor current here. So if we do the integration for the IC here and substituting IC equal to delta I over 4 for it, then we can find what is the delta VC in equation 53. Okay, you can either use the switching period T or the switching frequency F to do the calculation. But normally this will be the final value that, yeah. If you want to design something, normally people will be more interested on the switching frequency rather than telling you in time. So by substituting the delta I for either equation 51 or 52, you can then find the delta VC in equation 53 here in 54 or in 55 respectively. Both of them can be used to do the calculation for your delta VC. Okay, this is actually eliminated the delta I if you don't know. Condition for continuous current and voltage. Now, if the IL is the average current, then the inductor ripple current delta I will be equal to 2 times the IL, yeah, which is true, yeah. So by using the equation 48, the VA equal to K VS, and the equation 52, we can see that this term here is equal to this one. By rearranging it, we can find what is the value L here in equation 56. This L here is actually called the critical value of the inductor. Yeah. This is to ensure that your current is actually continuous and it is minimum value of the inductor. However, LC is not your desired value. Most likely, it's not your desired value. Okay, it just to tell you that this is the minimum value of L that is needed in order for your current to be continuous. Okay, the same thing applied to the capacitor here as well. The average, the delta, the capacitor ripple voltage delta VC is equal to 2VA here. So do the same thing by using the equation 48 and 55. We have this one, and arrange it for the C. We have in equation 57 here. So this C here is also the critical value. This is to ensure that your this voltage value is continuous. Again, it's not your design value, it's the minimum value that is required. Yeah. Let us take a look on this statement here. The buck regulator require only one transistor. It's simple and high efficiency, greater than 90%, which is true. Nowadays, if you are buying the IC that allow you to do this buck converter, if you do it properly, most likely you can get 90 or over 90%. Yeah, do it nicely and properly. Okay, but if you simply do it, you won't achieve the 90% due to the losses. Yeah. The DIDT of the load current is limited by the inductor L. The input current is discontinuous. This is what we have already seen from this waveform here. The loop current is discontinuous because during the off time, yeah, there is no value here. And this is one of the downside for your your this buck regulator. Okay, a smoothing input filter is normally required to provide continuous condition. Okay, this is another another problem already, right? It provides one priority of output voltage and unidirectional output current. It requires a protection circuit in case of possible short circuit across the diode path. Okay, this is the conclusion. Take a look on this example one here. This example one here has the input of 12 volt. The required output average voltage is 5 volt at 500 ohm. The peak-to-peak output ripple voltage is 20 millivolt. The switching frequency is 25 kilohertz. If the peak-to-peak ripple current of inductor is limited to 0.8 amp, determine the duty cycle, the filter inductance, and also the filter capacitor, and hence the critical value of L and C. Now, some question they will actually tells you the peak-to-peak ripple of the value, either the delta V or the delta I in percentage, or in this case is in number. Okay, it give you the exact number, right? So you need to then based on the information to decide. The frequency given is 25 kilohertz. Okay, so based on the equation 48 here, because we know the average voltage, which is our desired one at 5 volt, and the VS is 12, so we can calculate what is the duty cycle K. In this case, equal to 0.4167. So based on 51, we can calculate the inductor value equal to this. The same thing in equation 53, we can obtain the capacitor value at 200 microfarad. Now the same thing, if you are applying the LC and CC equation, you can obtain both the LC equal to 5.83 millihenry and CC at 0.4 microfarad. Now I can tell you, you can in fact compare to the value here. This LC is the minimum possible value for your current to become continuous. So if you compare this value and this value is bigger than this value. So your design value is smaller than your minimum continuous condition. So in this case, you can say that your current is actually discontinuous. And if you compare this value with this value here, you see that this value is smaller than the design value. Your design value is 200 microfarad, which is much greater than the minimum continuous condition, and hence you can see that the voltage is actually continuous. Right? This is the two things that you can conclude. Right. So we move to the next one, the boost regulator. Boost regulator is the opposition of this buck regulator. Boost meaning that the output voltage is actually higher than the input. And of course, one thing you need to remember, the output voltage can be either lower or higher. The same thing applied to the current as well. If you are having a buck regulator, say, the output voltage is lower than the input, but the current somehow is higher than its input. Similarly, for the boost regulator, the output voltage now is higher than your input voltage, but the current is lower than its input, because this one is something to do with the equilibrium of your this power. Yeah, consider the entire converter is lossless, so the power must be matched, must be the same. Yeah. Again, in this boost regulator here, you can see that there are these uh, component used not much different from the buck regulator. The only thing is that the arrangement, yeah, the arrangement for the uh, diode, the inductor, and also the switch is actually rearranged, right? So in this boost regulator here, you can see that during the time at T1, the switch is actually turned on. What happened? The current flow through the inductor and then go to the switch and then return in this direction. So no current will actually flow through here. So during this period of time, your inductor L here is actually charging up from the Vs. So when the switch is actually turned off, what will happen? If the switch is off, so this part will be removed. This one become open circuit, so that the voltage from the supply Vs here plus the energy from the inductor L here will be transferred to the load through the diode DM here in this direction. Okay, so you can see this one is somehow work a little bit differently. Initially, switch is turned on, I use it to charge up my inductor. So I separate my inductor part portion to my load here. So when you are looking into your load side here, your current somehow is actually equal to minus your IA, or in other words, IA equal to minus IC, because in this case here, capacitor is actually release the energy to to charge up your this load. Okay, and when the switch is off, this value here plus this value here will be transferred to the load through the diode EM here, and hence you can see the voltage across this one is actually the value of Vs plus the VL here. So you can see output voltage should be higher than the input supply voltage Vs. This one is actually your diode voltage. Is in fact your voltage across the switch. Okay, so when the switch is actually turns on, so you have nothing here because they are short circuit. Yeah, when the switch is actually off or open, then you see there will be a voltage appear across it, being that this gradient here is due to the value of your Vs plus your VL here, so it increase like this. Okay, and also for your supply current, in this case here, your supply current is similar to your inductor current, so your current will then be rising when the switch is turned on. Okay, inductor is charging up until this point. When the switch is turned off, the inductor is actually release the energy, so the current is actually reducing, right? And then the cycle continue. Whereas for the I1, the I1 is in fact the current flow through the diode here, the diode here. Okay, so during this period of time, because the current all flow through the diode, all flow through the transistor, so there is no current flow through the diode, so there is no value. This curve here is due to the discharging of your inductor plus the value from your Vs, so that it follows this curve here. Okay, so initially your capacitor current IC is following your IA, but it's in negative. This one can be actually seen based on this one. Okay, so my my IC equal to the negative value of IA. So when the switch is actually turns off, then this one you jump to its maximum possible value. This maximum possible value is in fact this value, this value here minus your VA. Okay, so you at this point inductor discharge the energy, so the current actually gradually reduce to certain value up until the end of the time T2. Then the T1 is turned on again, then it go down again to equal to the VA IA. Okay, so the cycle continuous. Then this is your VC. The VC should actually fluctuate in between the minimum and the uh, maximum value of this delta VC here. Okay, according to the current. Okay, so again, the output loop current should be continuous. Now, if we are based on the KVL here, when the switch is turned on, we have this equation here, and then delta I is equal to your I2 minus I1. So you have the equation 58 here. Arrange it for the T1, you have 59. Okay. Also, when the switch is actually turns off, yeah, you have this KVL equation for your entire circuit, which is equal to this one. And if you do some arrangement to it, you find what is your T2 here in equation 61. Right. And also equate the delta I for both of this equation here, give you this one, And if you substituting the same thing, T1 is equal to KT and T2 equal to 1 minus KT, that should give you this equation. Okay, so based on this equation here, you can see that the output average voltage VA is in fact equal to Vs over 1 minus K. So as the K value is small, say 0, so your output voltage is equal to Vs. If you have the value that is say 0.5, you can see that your VA is actually higher than your Vs. Of course, again, we have already studied in the chapter 6 for the step-up converter with the change of the large value of your this duty cycle K here, you can see that your output voltage is very sensitive and very large. Okay, so normally this K value for this kind of boost regulator normally shouldn't be too high. Yeah. Right. So the if you arrange it a little bit, you found that 1 minus K equal to this equation here, and substituting the K, which is equal to T1F into this equation here, just give you the equation 64 here for your T1. If the converter is lossless, input power equal to the output power, then your supply current can be obtained in equation 65 here. Okay, again, switching period T is equal to T1 plus T2. Based on the previous two equation for the T1 and T2, it gives you T equal to equation 66 here. So if I rearrange it to find for my delta I, we can calculate the delta I in either 67 or 68 respectively. Okay, they are the same, being that the 68 is actually the elimination of your VA. So our VA here, we can actually get our VA here, which is equal to this one. Substituting this one to your VA, that should eliminate it and then give you the 68. So the delta VC is the integration of your inductor capacitor current IC, and hence you you have uh, IA T1 over C in equation 69. Okay, substituting the T1, which is equal to this one into it, you found that your delta VC is equal to 70 here, or 70 by eliminate the VA 71. Okay, condition for continuous current and also the voltage, same thing, delta I is 2IL. So if I using the equation 62 and 68 here, we form this equation. We arrange it for the L, we obtain what is the critical LC here in 72. Similarly for the capacitor value, so delta VC equal to 2VA, and using 71 here, we have this. If we do some arrangement to it, we can obtain what is the CC here in equation 73. Okay. So I believe even though there are many equations for this topic here, but most of them can be derived or can be obtained based on a very simple rule, the Kirchhoff's rules, okay, the KCL and also the KVL. Okay, a boost regulator can step up the output voltage without a transformer. Okay, due to a single transistor, it has a high efficiency. The input current is also continuous. This one we can actually realize from here. Okay, because the supply current is equal to the IL due to they are in series, so the supply current is now continuous. However, a high peak current has to flow through the power transistor. Okay, the output voltage is very sensitive to changes in duty cycle K. It might be difficult to stabilize the regulator. The average output current is less than the average inductor current by a factor of 1 minus K. And a much higher IMS current would flow through the filter capacitor, resulting in the use of larger filter capacitor and a larger inductor than the buck regulator. Okay, which is true. Okay, so for this boost regulator, the size and the value of the L and C will be higher as compared to the buck regulator. Yeah. Okay, take a look on this example 2 here. A boost regulator has the input voltage of 5 volt, the average output voltage is 15 volt, and also the average load current is 0.5 amp. The switching frequency is 25 kilohertz. If L is 150 microhenry, determine the duty cycle, ripple current, and peak current of your inductor, the ripple voltage of the filter capacitor, and also the critical value of L and C. Now in this case, they are giving you the L value, but now you want you to find those things together with the ripple voltage. Okay, so the solution easily, okay, you can obtain the duty cycle K based on the equation 62 here, which is equal to 0.6667. Equation 67 should provide you the information to calculate the delta I, which is equal to 0.89 M. In equation 65 here, your IS can then be obtained based on the equation here. So you have 1.945. In 71, delta VC can be obtained, which is equal to 60.61 millivolt. Okay, based on the VA over IA, you can actually obtain what is the resistor R here, which is equal to 30 ohm. So from here, you can calculate what is the LC and CC in these two values respectively. Right. Based on this LC value here is 133. The value given to you is 150. So you can see that the current is continuous. Right. So this is what I can comment because the capacitor value is not given in this case here, right? So yeah, the capacitor value in fact is given to you is 220. That's right. It's saying I should put in this value here, but I have the value here to you. The C is 220. So based on this value and you compare to the critical value, the design value is much higher than this critical value, so that your this voltage is continuous. Regulator called buck boost regulator. As the name implies, you see that This buck boost regulator can provide the output that can be either lower or higher than your input voltage. When you are looking into this circuit here, you can see that they are basically nothing much uh, difference from the previous two topology. The only thing is that the arrangement of your transistor, your inductor, and your diode only. So in this case here, for the buck boost regulator, the Q1 is actually connected in series to your VS, and your inductor is now connected after your this Q1, but it's in parallel to your this VS here. The diode DM here having the reverse connection, okay, as shown in this figure here. Now, when the switch is actually turned on, what will happen? The current flow in this direction. So during this period of time, you can see that the inductor is charging up. And of course, the diode DM here is in this connection, so that you can see the current cannot flow through this diode DM here due to the reverse bias of the diode. Okay, and hence when in mode 1, you also separate the circuit into two parts. One is like this, inductor is charging up, then your this capacitor and your load is connected in parallel. And in here you also can see that your IC or your capacitor current is equal to the minus of your this load current IA. So in this mode here, when the switch is turned on, you see that, okay, when you are measuring the voltage across the VM here, there will be something there. Yeah, that provide you something. And the inductor current is actually rising up because of the charging up of this stage. And also during this period of time, your this diode current I1 here is 0 because of reverse bias. And as from the mode 1 circuit here, you can see that the IC equal to negative IA. Okay, so your IA is actually equal to this value here. In this period of time, assuming that this is a steady state condition, okay, so that your current, sorry, your voltage VA during this period of time, it will actually fall down, okay, fall down, and fall down until this point when the time at t equal to kt, when the switch is turned off. When the switch is turned off, it change state. Change state in here, you see that this is the minimum. When you change state, your this capacitor is now charging up. Okay, so that you can see that the initially the current is actually jumping from the minus IA goes to I2 minus IA. I2 is the maximum value of your this inductor current, okay, when the switch is turned off, because at this period of time your inductor already charged up at this period, at this level, like this one here, right? So your capacitor voltage is actually starting to charge up again. Okay, anyhow, the capacitor voltage will always fluctuate in this delta VC here. This delta VC depends very much on the value of the capacitor. Okay, if you have a large value, you see that this delta VC will be smaller. If you have a small value of the capacitance, your this delta VC tends to be bigger. Okay. So when the switch is actually turns off, when the switch is turned off, you can see that initially the charged up inductor release the energy in this direction. Okay, so it forces your current to flow in this direction. This is due to the diode here you connect in this way so that it force your current to flow in this way. Okay, and hence when you are measuring the voltage here, if I'm placing the probe across the load in this manner, this one is positive, this one is negative, I will measure a negative value of my average output voltage. Yeah. Okay, so this is just the theoretical, I mean the concept of how this buck boost regulator circuit is working. Yeah, when you are explaining on this negative part, the same thing, the inductor current should actually fall. Okay, from its maximum I2 value going down up until at time equal to 1 minus k times t. So the next cycle is actually turned on again. That when it turn on again, the inductor is charging up. Okay, during this period of time, you can see your this diode current I1 here, it should follow the inductor current here. Yeah, because they are in series. So this part for the this IC here, IC you actually jump, okay, from the minus IA to I2 minus IA. Okay, inductor for the inductor, sorry, for the capacitor, the current can actually change instantaneously, but the voltage cannot. That's why the voltage it takes a little bit slower time to react. Okay. In terms of their this equations here, once again, if I'm writing the KVL based on the transistor is actually turned on, I have this equation. Do the arrangement, I have my T1 here. So the same thing for the mode 2 when the switch is turned off. So I have this equation here, and do the arrangement, I have the T2 in equation 77 here. So equate the delta I for both equation 75 and 77 here, it gives me this equation here. And also, if we are substituting T1 equal to KT and T2 equal to 1 minus K times T into this equation here, and we do some arrangement, then we found that the average output voltage is equal to equation 78 here. And take note that there is a negative here, which is correct because the output voltage here is actually reverse the polarity. So in also in this if the circuit is lossless, we can found that okay, the supply current is equal to equation 81. This is actually based on the derivation from here. Okay, switching period t equal to t1 plus t2, substituting the previous two equation, and we found the equation in 82 and do the arrangement to find the delta I. We can either use 83 or 84 to obtain the delta I. 84 is we are substituting the VA, which is equal to this one into the equation, and hence it eliminates the VA, so you left only the VS. Again, the delta VC is actually the integration of your inductor current here. Okay, so this is also equal to your average current. So if we integrate this value here, we have this equation in 85. So substituting T1 equal to this one into the equation here, it gives us delta VC equal to equation 86. Or eliminating the VA, we have the delta VC in equation 87. Either one could do. You can use any of this equation to find your delta VC. for continuous mode conditions. Okay, this one is also the standard. Okay, by using equation 78 and 84, you form this equation. Do some arrangement for your L. This L is in fact your critical value of inductor. Okay, in equation 88. When you are comparing this equation here, you see that this equation is actually similar to the one in the buck regulator. Yeah, and also to find the critical value of the capacitor, we have to use the equation 87, and we have this one here. If we do some arrangement for the capacitor C, we form this thing in equation 89. So you also check that this the critical value of the capacitor is in fact similar to the one in the boost regulator. Okay, hence you can see that the name buck boost regulator is actually the combination of the two. Okay, buck boost regulator can provide output polarity reversal without the use of a transformer. It has very high efficiency. Also under fault condition, the GIDT is limited by the inductance L here. The output short circuit protection will be easy to implement. This is true also. Okay. There is a problem. The problem is that the input current is actually continuous. This one can reflect from this circuit here. When the switch is turned on, you have the current flow through, so there is a current during the time t1. But when at time t2, this switch is actually turns off, so there will be no current. So this the IS is actually stopped, and hence you see that for one cycle, the supply current IS is actually discontinuous. Right, take a look on this example 3 here. This buck boost regulator has the input voltage of 12 volt. Duty cycle is 0.25. Switching frequency is 25 kHz. The inductance is 150 microhenry. The C is 220 microfarad. Average current is 1.25 amp. Determine the average output voltage, peak to peak output voltage ripple, and also the ripple current of inductance, the peak current of the transistor IP, and the critical value of L and C. So this is actually your equation here, right? So based on the equation 78, you found that your output voltage is equal to -4. From equation 87 as well, you can obtain what is the delta VC, which is equal to 56.8 millivolt. Also from the equation 84, delta I can be obtained, that is equal to 0.8 amp. For the part D, the peak to peak current of the transistor IP is then equal to this equation, and hence it gives you 2.067 amp. IS is the average duration of the time t1 only, or kt time. Yeah, and the resistor R, you can obtain it based on this equation, because the load is resistor only, so you use the Ohm's law, V over I, to obtain it. So that should give you 3.2 ohm. From this value, you can find what is the LC and also the CC here. Okay, so based on this LC, you can see that this LC is much greater than the value that we use, which is 150 microhenry here. So your current is actually discontinuous. But for the capacitor, the critical value of capacitor, the CC, you obtain 56 microfarad, but the one that we use is 220 microfarad, so the voltage is continuous, right? Right, we continue to this choke regulator. Now, the choke regulator is in fact an advanced this version as compared to this buck boost regulator. Instead of using one capacitor and also one inductor, in this choke regulator here, it employed two capacitor and also two inductors. How it advanced? How it advanced? It advanced in such a way that it can provide a continuous supply current, which is the buck boost cannot be. Okay. Um, this choke regulator is actually named after the inventor called Choke. Okay. When you are looking into this choke regulator diagram here, you can see I have one inductor here. I do also have another inductor here. The capacitor, I have one here. I also have another one here. Okay, so how does it work? Well, normally we should assume that the Q1 is on and the Q1 is off. So we normally should have two modes. Mode 1 when the switch is on, mode 2 when the switch is off. Okay, but when you are looking into this circuit here, before you turn on or off of the Q1 here, if I just switch on my power supply, what will happen? If I switch on the power supply, there will be a current flow through in this direction. Okay, so the minimum value of the C1 will then be charged up through the VS. Consider that if we are actually putting this turn on my this regulator without any switching for a long time, your inductor L1 should actually become short circuited. Yeah, so that your C1 should actually charge up with the VS value only. Okay, right, we don't actually look at this one, we just look at it work with continuous switching conditions. So that means that they will turn on and off according to a given frequency, right? So we say that when the switch is turned on, the inductor L1 here will actually charging up from the supply VS here in this direction. Okay, in this direction, and at the same time, your C1 will actually release the energy through the transistor Q1 here to the load here, and then come back through the inductor L2 in this loop. Okay, so you can see that if the current flow in this direction here, so your diode DM here is actually omitted because it is in reverse bias, and hence you see the circuit in mode 1 here. The DM voltage, the diode DM here is actually omitted. This line is actually represent the switch on of your transistor is actually short circuited. Okay, so you have this loop. This loop here enable your L2 to charging up due to the release of the energy from the C1. Okay, and also when the switch here is actually turns off, yeah, what will happen? The supply Vs here plus the inductor energy initially stored in this mode 1 here will be transferred to the capacitor C1 through the diode DM here in this direction. and hence you can see that your C1 having the value that are greater than your Vs, which is equal to the Vs plus your EL here, right? And at the same time, during this mode 2 here, the diode DM also provide a path for the inductor L2 here to discharge the energy to the load in this loop here. Okay, so it's a little bit complicated as compared to the previous three cases, but it's kind of uh, interesting and logic. And also you can see that when you're looking into this diagram here, the supply voltage has no direct interaction to your load. Okay, everything is actually through the capacitor C1 to charge and discharge the energy uh, through the switch or through the diode DM here to transfer the energy to the load. Okay, so apart from that, you also can see that when your transistor Q1 is in on state, your this DM here is then omitted or it turn off. When the transistor is in a off state like this one, your diode DM here is then in a forward bias condition. Yeah, so you can see that the diode DM is in fact working synchronized to your transistor Q1. Okay, this one is VT here. VT is actually the voltage across your transistor here, right? So during this period of time when the switch is turned on, the switch is short circuited and act like a wire, so there's no potential difference between the 2 points, so there you don't see any value. Whereas for the diode VDM here, the voltage diode here, sorry, the diode voltage here, okay, you see that there is some value here. Okay, this value is in fact equal to your capacitor voltage C1. This one can actually see if I measure this 2 point when the switch is turned on. Okay, when I measure this point with respect to this point is in fact is this point, and this point is in fact this point. So I'm measuring the negative value of my capacitor C1, and hence you have this one here. So during the turn on time, your inductor L1 will be charging up from its L11 to L12, so minimum to its peak value. The same thing for the inductor L2 here. The current will be charging up from IL21 to IL22. Okay, this one can be reflect here when the switch is on. C1 is discharging the energy in this loop so that it is also charging up the inductor L2. So your L2 is actually charging up, so your current is a positive gradient. Right. And also during this period of time, your C1 is discharging the energy, so you have some value starting from 0 to flow to certain value up to the time equal to KT here. And when the transistor is turned off, you have the mode 2 here. The transistor is turned off, energy from Vs plus the inductor L1 here we transfer to the C1 through the DM. So the C1 is actually charging up. Okay, and your this L1 is also in its discharging process, and at the same time your L2 is also in its discharging process, so that it flow through it discharge the energy through the DM here to the load in this loop and direction here. Okay, so you can see that there is nothing here for your diode DM. Okay, because it is in forward bias, so it just act like a short circuit. You don't see any value here, but you do measure some voltage across the this transistor. This value is in fact equal to your Vs minus your VL1 here. Okay, the inductor for both of the inductor L1 and L2 also in its discharging process, okay, release the energy, and at the same time for the this capacitor, the capacitor discharging energy from this period of time, and then during this period of time it changed the polarity because it's now under the charging up process. So the current starts slowly to build up to approach to its zero value. What happened? What does it mean when you approach to the zero value? When you approach the zero value, meaning that um, the capacitor is actually fully charged. Of course, in this case, it may not actually work in such a way. It may charge up to certain value, and then the switch already uh, turns on again. It will then discharging the energy. When discharging the energy, you suddenly change the state, starting from zero to discharge the energy. So the current of the capacitor is essentially rising up. Okay. So taking this mathematical equation here, uh, here we have a little bit more complicated compared to the previous three cases here. Right. In this case, we assume that at time t1, okay, your inductor L1 is in action. Okay, so your Vs is then equal to the L1 times delta I1 over T1. This delta I1 is actually the change between the maximum and the minimum value of your inductor L1. Okay, do the arrangement, you have T1 in equation 91. Also, um, when the switch is actually turns off, okay, the energy from the supply plus the inductor will then be actually transferred to the capacitor. So if I am writing the equation, the KVL equation for this loop here, this loop, okay, this loop here, I have this equation here. So if I am doing some arrangement to it, I can then see my T2 is in equation 93. Okay. So of course, the VC1 is actually the average voltage of the capacitor C1. Okay. So from equation 90 and 92, 90 and 92, my delta I1 for both can then be equal to this equation here. If we do some kind of the arrangement, we can find that my VC1 here is equal to Vs over 1 minus K. Of course, this one you need to substituting the T1 and T2 equal to KT and 1 minus A times T respectively into this equation in order for you to find what is the VC1. Okay. And also, taking a look on the second inductor, the L2 here. This one also kind of similar when doing the um, this switch is actually turns on, okay, the capacitor VC1 discharge the energy through the load and also at the same time charging up the L2. Okay, so if we are looking into this KVL equation here, we have this one. If you do some arrangement to solve for the value for the T1 here, we have equation 96 here. The same thing for the when the switch is actually turns off. Okay, the inductor L2 is actually discharging the energy through this loop here, through this loop here. Okay, if I write the equation here, I have this one. So arrange it for the T2, I have equation 98. So if I equate both the delta I2 for the two equation here, I have this one, and then do some arrangement, I can also find what is my VC1 here in equation 99. So I have two VC1 value. One is in equation 99 here, which is this one. The other one is actually in equation 94, which is this one. So if we equate the VC1 for these two equations, we can eliminate it. And so we can then link what is my input and my output is. And this is actually shown in the equation number 100 here. And hence, you can see that my VA is in fact equal to KVS over 1 minus K. Of course, there is a negative value. This negative value will just reflect that the current is actually flow in this direction, either for when the switch is actually turns on, the discharging of the capacitor C1 here, or the switch is turned off, so your inductor, your this diode DM here is in action, the energy from the L2 is transferred to the load here in this direction. Both also negative, so you can see that there is a negative sign here. Okay, now K can be obtained in equation 101. Okay, based on this arrangement. And also, if you want to find what is your 1 minus K, the 1 minus K can also be obtained in this equation 102 here. Okay, this K and 1 minus K allow you to find what is your T1 and your T2 later on, if you want to. So assuming that the circuit is lossless, so input power equal to output power, and hence I can find what is my supply current IS in equation 103. From equation 91 and also 93, I can see that my T is equal to this equation 104 here. Okay, if we arrange or we want to find the delta I1, we can actually do some arrangement. We can find our delta I1 in either equation 105 or 106. Then normally we like to use this one. So we eliminate what is the VC1 here. The same thing in equation 96 and 98. We also can form another set of the switching period T, which is equal to in equation 107, this one. Do the arrangement, we can then find what is my delta I2 in either equation 108 or 109 here. So basically here you have two sets of the inductor peak-to-peak ripple currents, the delta I1 and also the delta I2. So the same thing applied to the capacitor as well. In order to find the delta VC1 here, we can actually based on this integration, we obtain what is my delta VC in equation 110 here, substituting the TS from the previous equation like this one, this equation here into here, we can then find what is my delta VC1 in equation 111 or in 112 by eliminate the this VA. Another delta VC is the delta VC2. We can also obtain it based on the equation 113 or in 114 here. For continuous conditions, it is also the same thing by using equation 103 and 106 here. We have this one. To find the critical value for the inductor LC1, we can use this equation here 115, or if we want to find the LC2 here, we can use the equation 116. You please help yourself to clarify how to actually find out each of these LC1 and LC2 based on the description of this slide here. So for the critical value of the capacitor, also the same thing. Yeah, the delta VC1 is having the average value of 2VA, the peak to peak. Okay, so we have this equation here, and those are arrangement. I can find my CC1 in equation 117, and also based on the equation 100 and 114, we can find the CC2 here in equation 118. Okay, so in this choke regulator here, the choke regulator provide input current which is in continuous conditions. The circuit has low switching losses and high efficiency. When Q1 is on, it carry the currents of inductor L1 and L2. As a result, a high peak current flow through the transistor Q1 will be incurred. Because the capacitor provides the energy transfer, the ripple current of the C1 is high. The circuit also requires an additional capacitor and inductor. So we have two capacitor, two inductor to work with. Okay. Take a look on this example 4 here. We have the supply voltage equal to 12 volt. The duty cycle is 0.25. Switching frequency is 25 kilohertz. L2 is 150 microhenry. C2 is 220 microfarad. The energy transfer capacitance C1 is 200 microfarad, and the inductor L1 is 180 microhenry. Current is 1.25 amp. Determine the output voltage, input current, peak to peak ripple current, and also the voltages. And then the final one is the peak current of the transistor IP. So based on the equation provided, we can find what is my VA here, which is equal to minus 4 volt, similar to the one in the buck boost regulator, because the question I think is kind of similar, just that it provides you with the additional of this L and the C values. IS is equal to 4.2, 0.42 based on equation 103. In equation 106, you find what is the delta I1, which is equal to 0.67. Delta VC1 from equation 112 is 63 millivolt. The delta I2 is equal to 0.8. Delta VC2 is equal to 18.18 millivolt from equation 113. The average voltage across the diode can be obtained based on the equation 119 here, okay, which is in fact equal to your VA. For a lossless circuit, your IL2 is then equal to IA in equation 120 here. So you have 1.25 amp for your IL2. So your peak current of the transistor is the summation of all those parts here. Okay, some part is due to your supply current. Some part is actually due to the discharging of your inductor L2 here, and plus some portion of your this time due to this delta I1 and delta I2 here. So when you add up it gives you the IP equal to 2.405 M.
Okay. What a lengthy video here. Okay. So far, any question you would like to discuss, or you have some doubt would like to uh would like to discuss here? Hello, anyone? Or you don't actually hear? Okay, good. Brian, no question, huh? Adin, everything okay? So you understand the concept. If I have the question, something like that, ask you to design uh this seasonal power supply, regardless whether it is a buck boost, or choke regulator. Can you do that? Not sure. Huh? Uh, anyway, I believe it is not very difficult. It's not very difficult, but um, it takes time for you to read, and this one involve a lot of this equation, I would say. But if I guide what, Weng, your question always got double meaning, ambiguity, huh? I can guide you, but you also need to help yourself, right? Huh? I think this four topology, the first three is considered quite straightforward. The only thing is the last part, the last topology, the choke regulator, that involve using two inductor and also two capacitor. Now, what I can say is that for the choke regulator, it is in fact a very advanced type of regulator compared to the buck boost regulator. Yeah, and you also can see that the input and output is actually not linked. They are not linked, uh, but they are actually using the this capacitor C1 as a energy transfer medium. Okay, for from the input to the output itself. Okay, a bit complicated lah, I would say, but um, not to the extent that you cannot understand. It is quite all right lah. Yeah, from what I can see, if you are willing to use some of your time to sit down and then have a think, there should be no issue. Huh? Hmm. I think that's it for the chapter 7 here. This chapter 7 SMPS. Um, no question. Sure, no question. Tutorial baru tahu. Ayo, itu tutorial for this one is very straightforward one. Tutorial only 4 questions for this chapter. Each topic got 1 question, and the um this tutorial is very straightforward for this. But when it comes to the questions, then you may find that especially in the exam questions, maybe you need to take a look on the exam question, then only you know what exactly uh, I mentioned. Uh, because under the the actual conditions when there is a question in the exam. The normally they will not provide you with the value of capacitor and inductor values, for example. Okay, but they will provide you with only the requirement. For example, okay, I need my output to be how much power, say, based on that power, then you may need to actually go and calculate um, the the inductors and also the capacitors values accordingly. Then the switching frequency, um, quite subjective. Sometimes I can fix the value for you, or I can ask you to choose. If I ask you to choose, then there will be uh there will be no exact solution. Okay, it depends on the frequency you use. And still remember, when you are doing your lab experiment, normally if you are designing something, your switching frequency must be actually at least how many, at least how much and why. Your frequency must be somewhere at least 20, 25 kilohertz, isn't it? At least, why I say so and why. Yes, yes, you need to have something that high enough so that human ear cannot hear. Mm. Yeah, yeah, at least you know, good. So at least over 20 kilohertz, okay. So that's when the design that you make, okay, people when use it, people don't feel like scared when use your product. Uh, well, you are bad at studying. Everybody also the same lah. I also don't like study one. You never mind lah. Okay, you keep going now. Don't like study, but force yourself to study a bit lah. Huh? Okay, so I think that's it for today. Thank you for your attendance. Yeah, you may leave now. Thank you. Okay, Friday, your big day. Okay, bye bye.